So far, we've discussed only bivariate regression, and so today I'm going to change over and include a few extra predictors. But before I do that, I want to talk about what happens when we include additional predictors. Now, many of you have already seen this in your introductory regression class, but this is, again, just a review of the material from Intro to Regression. So, first thing I'm going to do is I'm going to use a package called CAR, which is the Companion to Applied Regression. That's John Fox's his package that's associated with his book. And I'm going to create my own data set. I'm going to delete the old one and create my new one, and just give you a general sense of what I'm doing here. I've created a data set with 4 predictor variables, x1, x2, x3, and x4, and 1 dependent variable. And I can go over this later on, but essentially what I'm doing is I'm adding noise or error to my dependent variable to create my predictors. I want to make sure that I have a relationship between my predictors and my dependent variable. And I'm going to discuss each one of these in a little bit. But at any rate, how do we differentiate between bivariate regression and multiple regression? Well, as I showed you before, bivariate regression is really simple. I'm going to run this and I'm going to show you that in essence we have a very simple model where R produces, here's a correlation, I'm looking down here in the bottom, here's a correlation between Y and X1. And the correlation between Y and X1 can be seen in this bivariate relationship and in a regression where X1 is my predictor for Y. And as I mentioned before, right here, this is an unstandardized correlation coefficient. This is the standard error and the t, and we've already calculated this from last week. Now, what I'm going to tell you that's going to be slightly different is that this multiple r square right here, this is the amount of variance of y that can be explained by x, or in this case, x1. And this is a squared r value, and it turns out to be helpful when we're interpreting regression results, although there's some controversy about that. But at any rate, we're going to focus on that because psychologists use r square and adjusted r square to interpret regression results. So here you have the multiple r square, and the multiple r square, if you notice down here, what I've done is I've taken the correlation between y and x1 and I've just squared it. When I square it, I get 0.49. which is, or 0.50, which is essentially what I have here. It is identical. And then when you adjust for it, you adjust for it for sample size and number of predictors. And so almost always it goes down. So what we have here is a simple bivariate model. Okay, now if I go back to my original data, and what I'm going to do is I'm going to run my model now, my regression so predicting y, and I'm going to use x1 and x2. And what do I get? I'm going to go through all these results. Oh, I never loaded my car, so I have to go back up here. Okay, there we go. So we'll do that. Okay, so what do I get here? So the first thing is I have 2 predictors now. I have x1 and x2. And x1 and x2 are both significant predictors of y. And I have an adjusted r square, or a multiple r square, we'll focus on that, of 0.62. That's right here. And if I take a look at my correlation, my bivariate correlation between y and x1 and y and x2, you'll see that they're pretty high. See, x1 is correlated with y about 0.7, and x2 is correlated about 60. So now what we have is we have 2 strong correlations, and both of them are significant predictors because they're independent. The shared variance that they have is with y primarily. And how do I know that? Well, I use my function from the CAR library, VIF, which is variance inflation factor. And the variance inflation factor because there are only two predictors, these are going to be identical, is 1.16, which means that our standard errors are going to be inflated a bit because of the slight correlation. Ideally, we'd want it 1.0. That means that x1 and x2 would be independent, and variance inflation, or VIF, goes up to some infinite value. So you can have really high values. The higher values of VIF means that you end up having multicollinearity problems, and what happens is the R square is not, it tends to be distorted based upon the shared variance between our predictors. So multicollinearity affects R square. It also affects the standard errors and thus hypothesis testing. So I'm going to run these other ones, these other linear models, and I'm going to go through each one of them separately. So my LM22, that's what I'm doing here, is I'm just adding an additional variable. So LM22, what I've done here is I've added, now I have x1, x2, and x3. And now look what happens. x1 used to be a significant predictor, but as soon as I throw in x3, it's no longer a significant predictor. Okay? My multiple R squared for just x1 and x2, if I go back up here, you'll see that x1 and x2, both significant, and my multiple R squared was about 62, right? All right, so low 60s. We know that. Now when I have three variables, now we've crept up. So every single time we add a predictor, as long as the predictor actually shares common variance with the dependent variable, our multiple R squared is going to go up. And all that means is that we're accounting for variance in our dependent variable. And usually you can pile in a bunch of predictors and do a better job predicting y, but here's where you get penalized in the adjusted R squared. So the more predictors that you throw in, the more adjusted, the multiple R squared gets adjusted and adjusted down to reflect that. So what it is it penalizes you for the lack of parsimony. So take a look at VIF now. Remember, VIF ranges from 1, which is great, to an infinite value. I mean, they can be huge. Maybe not infinite, but very large. I've seen VIF as high as about 15 or 20 in practice. So look at this. We have 4.2. That means that VIF is a measure of association, and it's an index. And what it is it says that when x1 is a dependent variable and you're using x2 and x3 to predict it, there's a lot of variance that's shared with our other predictors, and it's mostly due to the common variance that's shared between x1 and x3. And the reason for that is I modeled it that way. You'll see here x3 has common variance with y and with x1. So x1 and x3 should be correlated, and they are. They're correlated, and now what we're seeing is we're seeing high multicollinearity, and when I include x3 in the model, all of a sudden VIF goes up. So now I've run now linear model 2.3, and linear model 2.3 is just x1, x2. Whoops, what happened there? Okay, and oh, I forgot to do the summary. I have a typo there. Okay, so let's just take a look at the summary. The summary, x1, x2, x3, and x4. Now I have 4 predictors in our model. Notice that multiple R squared goes up. As multiple R squared goes up, it's an indication that we're accounting for more variance in the dependent variable. But we're also getting slightly penalized for the adjusted R squared by having a less parsimonious model. And VIF for this, you'll see that x4 is an independent predictor, right? Look at this. This is just about 0. This is just about 1. So that means that x4 is not collinear with the other predictors. So that's a good thing. But x1 and x3 are definitely collinear. I'm running this one final thing. This is a nested model comparison, comparing the different models that I've run. So instead of just including the bivariate model, I have the two predictors, x1 and x3, x1 and x2. Then I add x1, x2, and x3, and then so on and so forth. And what it shows is that model 2 is significantly different and significantly better than model 1. So by including x3, we're actually benefiting. We're getting a better model fit. And the reason for that is that x3 is double dipping. You'll see this, and you'll get lots of practice in computing your own variables throughout the course. But you'll see here, x1 just has one instance of y, right? But x3 has not only one instance of y, but it also has another instance of y because I'm carrying over x1. So think of it as like a cake that you're baking, that when you add one part of flour and then one part of sugar and one part of eggs, right? You have 3 parts, so 1/3 of it is flour. But now if I have another cake mixture that I'm also including that has other flour in it, right here, that I'm getting more parts of that. And that's reflected in the overall prediction model. You'll see that x3 is the best predictor, and it's the best consistent predictor overall. If I have x3 here, you'll see here that I have the best predictor, certainly relative to x1. I believe, let's see, it just so happens that x2 turns out to be a really good predictor as well. So what we have here is a shift from standard bivariate regression to adding different variables to improve our prediction of y. So including more predictors means that we account for more variance of y, but we also run into problems when we include more variables that are potentially related to one another. And when that happens, we have collinearity, and that collinearity or multicollinearity increases the variance inflation factor. And what does that do? That turns out to affect the standard error of each of our estimates. And when standard error increases, our t-value decreases. Now, why is that? Because here, the t-score is nothing more than our parameter estimate divided by our standard error. So as this standard error increases, what we're doing is we're increasing the denominator. T goes down, and when the t-value goes down, the probability associated with that t-score goes up. Now think about hypothesis testing. In hypothesis testing, remember, everything's backwards. We always want p of less than 0.05. So when the p value goes up, that's a bad thing. All right, so now this is, again, just a refresh of introductory regression. In our next video, what I'm going to do is I'm going to talk about interaction effects and how those are interpreted and what they do. So stay tuned for more.